Okay, section 6.7 dot products. We're still dealing with vectors. Um, we're going to find the dot product, which isn't bad. The angle between the vectors is a little bit more difficult to follow, but it's something you can relate to. You've seen that before. Uh, Dot product to determine if two vectors are orthogonal. Here's a new term that you need to know. Um, just means perpendicular, by the way. Uh, we're going to not do projections. Um, we're going to skip the sum of the vectors that deals with projections, but we are going to do work. So we got a few things to go. This is not as bad of a section. All right, the dot product of two vectors um, of vector addition and scalar multiplication result in vectors. By contrast, the dot product of two vectors results in a scalar, just some number, some real number, not a vector. Um, all right, so and this is simply found. V times W is multiplying the first term of the both vectors and adding to the product of the second term of both vectors. More formulas, I know. So simply put, we're going to go ahead and run this. We've got V and W, so if we find V times W, that's going to be 7 times 2 plus negative 4 times negative 1, 14 plus 4, or 18. Part B, right? W times V, in other words, they're just reversing the order. So it's going to be 2 times 7 plus negative 1 times negative 4, or 14 plus 4, which is 18. And you notice that commutative property didn't make any difference there. All right, and then the last one, part C here, we're going to square the vector, right? It's W times W, which is 2 times 2 plus negative 1 times negative 1, or 4 plus 1, which is 5. All right, we have properties, as you just saw, that we've got this thing called the commutative property, right? Um, there's a distributive property, um, which means if we're going to add two vectors and multiply by a vector, that's the same as the distributive property, but we're still going to end up with a dot product, which means we're going to end up with a number. We've got the zero vector, that holds true. And when you square a vector, it's basically squaring the magnitude. Um, when you multiply a scalar times a vector, that's the same as multiplying the vectors and then multiplying by the scalar. Uh, either way, it's going to come out to be some real number, some scalar. Um, this is also true. We can regroup these and work with the associative property of multiplication. All right, now this is where it gets a little more fun, I think. The angle between the vectors. The law of cosine can be used to derive another formula for the dot product. This formula will give us ways to find the angle between the vectors. That's what we're looking for right now. All right, so I'm going to start out. Let me just write down the law of cosines. Okay, from there, what we want to do is we want to see if we can substitute in things that we know. For instance, when you square something, that's ultimately squaring the magnitude. Okay, so magnitude of u squared, we've kind of already seen that. Magnitude of v squared plus the magnitude of w squared minus 2VW. That V times W is your dot product, which is just going to be some number. cosine of A. And that's how that fits into the law of cosines. Now, um, by substitution, um, we're going to end up just substituting the dot product in for um, u squared, which we already know, we've seen that in the previous one. So that literally is just v times w equals that whole thing. Um, again, this is, I'm not doing all the substitution here, you guys. You can go back in your textbook and see how you go from one to the other. Ultimately, what we're doing, and again, there's 15 steps between these two. I'm not going to go through all that because you don't need to know it. V times W divided by the magnitude of V times the magnitude of W equals cosine A. And now you've got your formula for deriving an angle between the vectors. All right. That's what we were just looking at. That's what we just derived to a certain degree. Taking it to the next step, we end up with an inverse cosine dot product divided by the two magnitudes. All right. So we want to find the angle between the vectors, which means we've got to do some arithmetic. Now, keep in mind, you're going to write down the formula, and we want to find the inverse cosine of, and there's going to be some arithmetic in between, right? This is going to be we got to multiply the dot products divided by the magnitude, right? This is going to be V times W divided by the magnitude of V times the magnitude of W. And the question is, how do you go about doing that? We got some work cut out for us. Okay, I've done some of the grunt work for us. So therefore, inverse cosine of -2 divided by 5 root 5, right? And let's plug that into a calculator. So as you plug this into the calculator, two things. One, make sure you are in degree mode. Two, as you plug this in, you're going to want to put parentheses around the denominator. Otherwise, it's going to multiply by root 5. This all equals 100.3 degrees. And we found theta. So again, a bunch of arithmetic, really not all that bad. Two vectors are parallel when the angle between the vectors is either 0 or 180. So that sort of implies that the vectors are either like this, or maybe your vector is like this, just going the opposite direction. If theta equals 180, then the vectors point in the opposite directions. That's what that's saying up there. And you've got a good representation of these here. The two vectors are orthogonal when the angle between the vectors is 90 degrees, implying perpendicular angles, right? Or perpendicular lines. We know that the dot product can also be found by the magnitude of W times the magnitude of V cosine theta. If these are orthogonal, then this is going to be equal to 0. So again, I wouldn't go through this. I would just simply work with our dot product here. Okay, so we're looking for slopes, or we're trying to prove that something's orthogonal. Two non-zero vectors, v and w, are orthogonal if and only if the product is 0. All right, so I think you guys can multiply these. So I'm going to stop the video and then we'll show it to you. So as you multiply these, notice that their dot product is 0. Therefore, this is going to, these two lines or these two vectors are perpendicular to each other. Oops. Okay, moving on to work. The last couple of things. This is not bad. This is just a formula you're going to have to write down. This is saying that we're going to find some work multiplying the force times the vector. Notice that that implies the magnitude of a vector times the magnitude of a second vector cosine of theta. That's the formula you're going to want to use. Let's try it. Okay, remember, work is done by the magnitude of some force times the magnitude of another force times the cosine of theta. So here we go. We're looking for this stuff here. Kyle pulls a wagon along a level ground by exerting a force of 20 pounds. There's your first one. On a handle that makes an angle of 30 degrees, there's your theta with a horizontal. How much work is done pulling a wagon 150 feet? This is how I'm going to write this. This is going to be 150 times 20 cosine 30. Plug that into a calculator and you're off and running. All right, so plugging this into a calculator, 2,598 feet per pound is the work that's being done. That's all there is to it. Good luck. Have fun.